So record to the cloud, here we go. Right, so I shall shrink that down. Hope that you can see something or other. And so we now come to the session on relativity. And as a bit of background, we may remember that in session 3, we looked at one of the triumphs of the 19th century, I suppose, the discovery that light was a wave. And then what's more, it was a wave of electricity and magnetism, electromagnetic field. And then, though, problems started to arise. You may remember that there were issues in connection with issue of light from hot bodies, the so-called ultraviolet catastrophe, which meant that the wavelengths of the light that came out wasn't what the theory predicted. And there was also the strange phenomenon of the photoelectric effect, where light shining on a metal kicked electrons out, but it didn't matter how bright the light was, it only seemed to matter what frequency it was, which was very strange. So those two developments or observations led eventually to the whole strange bag of worms called quantum physics, where light turned out to be like a wave or like a particle or both, and then particles like electrons turned out to be like a wave or a particle or both, and it all began to get weirder and weirder. However, believe it or not, a little bit earlier than that, but only almost a few years earlier, the business about light being a wave spawned another lot of horrendous problems. And that's what we'll be looking at this time. Because although the way light had been determined to be a wave of electromagnetic fields, that was what it was a wave of, there was the question, well, what's it a wave in then? I mean, that's just empty space. Sound waves travel in air. What do electric waves travel in? Well, maybe there's some sort of substance throughout the universe called the ether, which is what waves of light travel in. Or maybe space, although it's nothing, actually is a sort of entity. Maybe the sort of weirdly is something there. You may remember that actually some of the early civilizations with their ideas of elements, you know, fire, water, earth, air, some of them had a fifth element which was sort of nothing. Well, maybe they were onto something. Maybe space is actually sufficiently sort of real that a field, namely a property of space that means that a force is exerted on something that's put there, is actually a real entity. Maybe that's what light travels in, sort of empty space as a reality that can actually have field values in it. Well, those thoughts were bubbling around, but then physicists, of course, began to think, well, if there is either this ether everywhere or a fixed or a sort of fixed space in which everything moves and exists, then we ought to be able to measure what speed the Earth's going through this mysterious ether, because we could do a little experiment of measuring the speed of light from a bit of apparatus on the Earth as the Earth tootles round the sun. So the Earth's going like that. And we measure, so presumably it's heading up this way, so we measure what the speed of light is going that way and compare it with the speed of light measured sort of across like that, which is not in the direction of motion of the Earth, and see whether there's any difference. And if there appears to be no difference, if in other words we happen to be just at the freak of a point on where the Earth isn't moving with respect to the ether, well, okay, we'll wait 6 months until the Earth's on the other side of the sun going in the other direction and do it again. And that will jolly well show something, won't it? So that was what was done, the so-called Michelson-Morley experiment, and it didn't show any difference. The speed of light seemed to be exactly the same, whichever way the Earth was moving. And then actually various people, including Einstein, began to think, actually, that's a bit weird. I mean, if you really do have a sort of fixed volume of space like this, which is sort of somehow fixed, and the Earth or anything could be hurtling through it at great speed and then emits light. I mean, supposing you're going at 3/4 of the speed of light already with respect to this frame, would you then see light have a speed of 1/4 of what we see? And wouldn't that mean that all the way electric and magnetic fields behave will all be different? So does that mean the laws of physics actually change according to what speed you're doing? In fact, he thought, if you actually are going at the speed of light, then presumably you'd see these electric fields, instead of rippling away from you, they'd be sort of frozen in space, wouldn't they? Just sort of sitting there. Well, that can't happen, or at least that's all very weird. The idea that the laws of physics vary according to how fast you're moving in some arbitrary sort of expanse of void, that doesn't sound right. That doesn't sound right at all. And so the idea grew, no, the laws of physics don't care what you're doing, don't care whether you're moving. So else you can't tell whether you're moving or whether you're still and the Earth's shooting away in the other direction. There's nothing to tell what your absolute velocity is. So wherever you are in the universe and whatever you seem to be doing with respect to other stars and galaxies, what you find as the laws of physics are going to be the same. So that was the suggestion, the proposal. The only thing is it started having awkward consequences. Now I'm just going to check this Zoom thing because I just want to see whether anybody has, no, I can't work out how to make it big. Sorry, I don't think I can do this. Oh, is that what it is? Oh yes, and there's nobody in the waiting room still, so good, I can collapse you again. Right, sorry about that little hiatus. So Einstein, though, took all the awkward consequences to their logical conclusions, and they didn't faze him, and he worked it all out, and it all worked. But now, a sort of example of the type of problems that occurred can be, and a lot of them were identified by just thought experiments. You know, Einstein, who was a patent clerk in Switzerland at the time, sort of ruminated at his desk and sort of really derived this initial theory just by sort of thinking about things. There was a thought that, okay, so the speed of light is always the same, whatever the source is doing. Well, supposing you have a sort of hypothetical situation of a spaceship with a weird little clock in it, which is a bit of a sort of hypothetical thing, but a clock which consists of a ray of light bouncing up and down between two mirrors like that. So it's sort of ticking, doo, 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 doo. It's bouncing up and down, of course, at the speed of light, which is extremely fast, but nonetheless, it's bouncing up and down. And synchronized with that are the clocks in the spaceship, the heart rate of the observer sitting there, and all of it is working in synchronism. And then supposing this spacecraft suddenly starts moving at a great speed. Well, now, as far as everybody's inside it is concerned, nothing's changed. So the light's still bouncing up and down, and the clock's ticking in synchronism with it, and they're all ticking along in synchronism with it. But to the point of view of somebody sitting on the Earth watching the hypothetically spacecraft shooting by, because it's moving, the light that bounces off the mirror at the top actually goes sort of diagonally like that, because the bottom mirror's moved in the meantime. And then when it bounces up again, it goes diagonally again because the rocket's moved even further. And so it goes on like that. And the trouble is, of course, this distance is more than that distance because it's, you know, the hypotenuse of the triangle. So according to this observer, the light has to travel further. And since both of them have the same view, the speed of light is unchanged, this takes longer, doesn't it? So the ticks of the clock as seen by an observer, so to speak, looking at the spacecraft hurtling by, have got slower. And what's more, so is everything else. The clock ticking in synchronism with it, and the people's heart rates and everything have all slowed down. Because if they got out of step with this, if somehow it was only the light bit that changed, then these people would be able to know that they had an absolute velocity because their clock was getting out of sync with the light thing. So everything stays in sync with this. So this person here sees the light clock, the ticking clock, the people, everything slow down. So in other words, says Einstein, well, time has slowed down then. What this person sees is that lot, their whole time is just going more slowly. Time isn't a sort of great big river flowing forward, taking everything at the same rate. It depends what you're doing. And if you look at something that's moving very fast with respect to you, its time seems to be running more slowly. Well, that's how it is then. Other people might have blanched at this, but Einstein, no, that's how it is. And what's more, by doing other rather elaborate sort of thought experiments involving trains trundling along and light being shone forward to a mirror and backwards, and meanwhile the train moves, he was able to divine that another thing that must happen if everything is to work is that if you are moving, if something is moving with respect to you, then distances in the direction of that motion are all foreshortened and shrunk. So if a ruler is coming towards you at nearly the speed of light, it looks much shorter than the foot that it would if it was stationary. Well, all right then, things shrink and time runs differently. That's what's necessary if you are going to maintain that the speed of light doesn't change regardless of the speed of observers. And then I think one of the interesting sort of things about this, which is all starting to get quite philosophical, is that suppose if one thinks of these, the hitting of the mirrors by the little ray of light as events, then the event of this hit, of A, and the event of that hit, and the event of that hit, those are all events in space and time. As far as these people are concerned, all these events, A and C, happen in the same position, but at different times. Whereas as far as the person here watching the spacecraft go away, events A and C happen at different times and in a different place. So, however, and what's more, not only is the place different, but the time he sees between these occasions is different from the time that this person sees between A and C. So time has changed, distance has changed, but intriguingly, there is a mathematical combination of the distance and the time between these two events, which all observers would agree on. So there is a combination of the distance and the time separating any two events in what began to be called space-time, which is constant. So the feeling is, or what was beginning to emerge, was that there is something called space-time. What on earth it is, we don't know, but space and time are less fundamental than space-time. And if you have two events separated in distance and time, A and C, if you imagine them in this sort of strange space-time world where maybe, and I shall draw little axes, maybe that represents one dimension of space and this represents time, what emerges is that this separation in space-time is actually constant. But different observers moving at different speeds see if you like, this distance is projected onto their axis. So this person sees not so much distance and a lot of time, whereas this one sees not much time and a lot of distance, if you get the complication. It's not actually quite like that. I'm afraid it's slightly weirder, but the principle is the same, that what seems to emerge is that there is such a thing as an absolute separation of events in space-time, but that any observer will see the separation as being a certain amount of space and a certain amount of time, depending on his speed with respect to these things. And different observers see it as having a different amount of a time element and a different amount of space element. So that was the first, as you can see, quite fundamental and strange result from what began to be called Einstein's theory of special relativity. That this idea of a four-dimensional space-time, which is the sort of real, and what we see as space and time are sort of aspects of that. It also emerged that electromagnetic fields, I've talked about electric fields and magnetic fields. Magnetic fields arise when a charge is moving. So again, if you're sitting stationary and there's a charge Q stationary with respect to you, all you see is an electric field. But if you're going past it, it appears to be moving, so you see a magnetic field as well. So once again, it seems that really there is an electromagnetic field, but how much of it you see as magnetic and how much you see as electric depends on your movement with respect to the charge. Very interesting. Well, further ramifications occurred. Okay, if you've got I think I won't go into, by rather sort of clever little arguments based on, do you remember the old conservation of momentum? You do another little thought experiment of two balls bouncing off each other, coming in like that and bouncing off each other like this. And then by clever little thought experiments of imagining yourself traveling along with this particle. So in other words, it seems to be just going up and straight down to you. And it now means that the other particle is coming in, well, I suppose actually that's, yes, perhaps they did it a different way. I think he did it more like this, it's coming in like that and going off like that, which means that if you're moving along with this one, the other one coming in is coming in at a massive speed and then clocking off again like that. because of it going at a great speed like that, its time is slowed down. It means that it's the component of its velocity in this direction is sort of slowed down. But if the conservation of momentum still works and it manages to bounce that one off straight up and straight down, then the only conclusion is that this thing looks heavier. So if something's going past you at a great speed, it looks heavier. And that led to the thought from old Einstein's amazing brain, well, maybe, perhaps, of course, when something's moving with respect to us, we say that it's got kinetic energy. You may remember right back from our first little session. Maybe the reason it seems heavier is because of that kinetic energy. Maybe the energy and the mass of it are actually rather similar. And this led to a sort of, again, a supposition, which eventually emerged to be definitely the case, the famous equation that some of you may have heard of, that the energy of a particle is equal to its total mass times the velocity of light squared. And that total mass is a combination of its what they call the rest mass and extra mass that it's got because of it having kinetic energy. So the total energy is a combination of its rest mass or rest energy and any other motion energy that it's got. So when we talked about the conservation of energy and the conservation of mass in chemical experiments, really that needs to be taken up a new level to conservation of mass energy, because you can change one into the other. This was yet another strange phenomenon emerging out of the theory of relativity. And a final one, perhaps, is that just as space, dimensions, and time seemed to be aspects of the same sort of thing, this mysterious space-time, so energy and momentum that we talked about in our first session, these funny concepts, also seem to be aspects of the same sort of thing. They transform between each other depending on the relative motion of an observer in the same way that space and time transform into each other. So here we have the strange situation that we've entered a new perception of the universe where space is replaced by space-time. Space and time are sort of aspects of the same thing. Energy and momentum are sort of aspects of the same thing. Energy being sort of momentum in time. What? And also mass and energy are interchangeable, are sort of aspects of the same thing. So it's really very strange. And that was really, I think, one of the main points of this screed, and to sort of the point to take away perhaps, is that Einstein published special relativity in 1905. In fact, the same year that he published his theory about the photon, quanta of light being responsible for the photoelectric effect, and published his paper about analyzing the motion of pollen particles in fluids, which demonstrated the actual existence of atoms. So he did 3 sort of Nobel Prize worthy efforts in 1 year, whilst he was a patent clerk in Zurich or somewhere. Rather fascinating, really. But the message is that that things have suddenly got quite a bit weirder. And just as a little aside before we move on, all of these things have been demonstrated, particularly with subatomic particles, that subatomic particles that have, in the Large Hadron Collider that have been accelerated to pretty much the speed of light, are observed to have lifetimes infinitely longer than when they're just sort of sitting around in the laboratory, if you like, because of this time slowing down when you're going past at a great speed. And the interchange of mass and energy is how you get these heavy particles that I may have mentioned in that last talk, where I showed that funny little diagram of the particles that make up the universe. And I mentioned that there seemed to be heavier versions of the same, which we didn't know why they were there, but they seem to exist. Well, you might ask, well, how on earth did we get them then? And the answer is we created that sort of thing in the Large Hadron Collider by wanging things in opposite directions to hit each other. So there's a huge amount of kinetic energy which is available, if you like, to be turned into mass. So you make heavier particles by wanging lighter ones together at massive speeds. So again, it has been amply shown by experiment that mass and energy are indeed interchangeable, and that when a heavy particle decays into lighter ones, the difference in mass is taken up by the lighter ones flying off at vast speed. It all works. Right. Well, that is a simple little special relativity. Well, now that turns out to be only half the story. Einstein then went on to his next theory, so-called general relativity, in 1915. Well, now this I don't really understand. I certainly have never done the maths of it, so I don't really understand it, but I've got a sort of enough of a drift of it to be able to give a faint hint. And it again is quite strange and introduce more weird sort of concepts. So I think again, we sort of go back to this idea of fields, because really all of these theories are very sort of field orientated. And it certainly did seem that with, for instance, electromagnetism, it really was a very good approach for us to try and calculate and sort of understand what's going on, to divide the effects into two aspects, what you might call the field equations and the equations of motion. So it really did seem to be the best way of talking about what happens if you've got lots of charges sort of in some space. What they do is set up a field in space round them, such that every point of this space, which it comes back to the idea of sort of assuming that there is something there, sort of, which has its qualities modified by the presence of these charges, such that if you put another charge here in the field, it experiences a force in that direction. So that is the laws, the equation of motion, that the acceleration this particle experiences is a consequence of its charge, and the field which is set up by this thing, the field being a quality of every point in space round it, which determines how much force a charge would experience. That seemed to work very well for electromagnetism. And so Einstein sort of really thought, well, can we do the same sort of thing for gravity and set up a field equation, because we haven't really got it very clear, not proper mathematically. So he worked on this and came up with the really rather extraordinary idea now that the field equations for gravity describe not so much a sort of a property of space in terms of something to do, something applying to each point in space, which means that a charge will experience a force, but mass, concentrated mass, if we now think of all of this as sort of bits of mass, that actually has the effect of distorting or curving space itself. So sort of space, little elements of space have sort of got distorted, a bit like imagining a very, very nice, perfectly elastic sheet, which you draw a straight line on, and then you push a globe up through it. So sort of like that. So it's sort of this globe is being sort of forced up through the sheet, which means that your straight line is going to do something rather weird now. And that is what he maintains is how to describe what gravity does. Gravity, due to these masses, distorts the sort of very fabric of space, except does space have a fabric? Well, perhaps it does. It's distorted by the presence of the mass. And the laws of motion are that anything that's moving will continue to move in a straight line, except that because of everything being curved, it doesn't look like a straight line anymore, because it's, now of course this is curved space-time, just to make life really difficult. The equivalent of traveling in a straight line in space-time is a trade-off between the shortest distance between 2 points and taking the longest time to go between them. There's a minus sign, so it's not the shortest time and the shortest distance, it's the shortest distance and the longest time traded off between the two. And that is going to be the path which something moving will take in the presence of the distorted space caused by mass. So I suppose, one can sort of vaguely imagine it, but supposing here's the Earth, and you're in a spaceship, and you are doing, that's what you would do if you were approaching the Earth from a distance. You'd be getting faster and faster and faster as you're being pulled in by gravity all the time. So you whip round here, and then you go away, slowing down as the Earth's gravitational attraction drags you back. So that's what, if you like, you outside would see, this thing coming in slowly, they were whipping round and then going off slowly the other side. But if you were in that spacecraft, of course, you'd feel nothing. And because it would be being attracted, so would you. So as far as you're concerned, you're just going along in a straight line, and this great big Earth thing comes and whoosh, comes by you, and you think, oh gosh, that was a near miss, wasn't it? But so to speak, as far as you're concerned, you've just carried on, and this thing sort of whopped round you. Well, I'm sure that's very trivial, but it's a sort of sense that the law of motion is you just keep going in your straight line, but because of gravity mucking about with space, your straight line geometrically now looks like something like that. So that is a sort of very, very crude, noddy introduction to general relativity. But it basically started with yet more sort of funny little thought experiments, one of which was to do with Einstein imagining a clock in an accelerating spacecraft, because you can't actually tell the difference between being on the surface of the Earth with the Earth pulling you down, or you being in a rocket, being accelerated upwards with an acceleration equal to the acceleration due to gravity on Earth. There isn't actually any detectable difference between the two. So he did another one of his thought experiments of imagining a clock in a rocket that was accelerating. So in other words, between each interval of that little bouncing light clock, the rockets moved further in. It moves an extra distance now between each of these bounces, and what's more, the distance changes because it's getting faster, because it's accelerating. And that led to the conclusion that clocks run faster when they're higher up, because of the Earth's gravitational field, because of the Earth distorting space around it. The further away you get from the Earth, the faster a clock seems to run. Well, of course, it's a very, very small effect, but it's definitely true, because all the satellites that make up GPS, which everybody's mobile phone and everything, and every single Amazon delivery driver will be absolutely finished if all of these things stop working, because there's no way you can actually read a map. It relies entirely on these little satellites tootling around, and they all have very, very accurate clocks, because the whole satellite nav system works by comparing the distance to the different satellites, which you only know by how long the signal's taken, and you have to know exactly when it was transmitted and compare that with when you receive it. So all of these things have to have very accurate atomic clocks on board and be continually transmitting what they think the time is. And all of that has to take into account the fact that because they're at this quite a big altitude, I can't remember, 67,000 kilometers or something, or was it 600, maybe 6, I can't actually remember. Anyway, whatever it is, the clocks run faster, and if that wasn't accounted for in the calculations, GPS and Amazon and mobile phones would all come to a nasty stop. So Einstein was quite right, and he, without his formulation, GPS would be a dead duck. So there we are. I think that's the main point of this and the previous one, I think, is to sort of illustrate how physics, I suppose, has always started, it has involved funny concepts. You remember right from the word go, we talked about energy and momentum and even mass and force and things like that. And then we had this concept of a field introduced to help understand things. But now, since 1900, things have got an awful lot weirder. We now have space-time, and we have bending space, and we have mass and energy being the same sort of thing, and all sorts of weirdness, quite deep, fundamental weirdness. Another sort of observation, really, is that it seemed to me, at any rate, that all of Einstein stuff, you know, special relativity, general relativity, all comes from the world of smooth, what you might call analog mathematics, and smooth curves and differentials and gradients and pure mathematics type of things, and real numbers and fields, whereas quantum mechanics was all about lumps and quanta and photons and shells and sort of not smoothly varying things, but lumps of things, and everything being in little lumps and sort of digital, if you like, rather than analog. So the two theories, relativity about the universe and quantum mechanics about the subatomic world, seem to be sort of based on completely different mathematical approaches. Can they be sort of stuck together? Well, that's what Mr. Ravelli and others in the strange world of loop quantum gravity have been trying to do. And I don't understand that at all. I haven't a clue what they're up to. But that is what they're working on. And I suppose I'm going to illustrate the sort of general views of the universe as seen through these different stages by a nice little diagram which Carlo Rovelli had in his book. So I'm going to replicate that. Share. Now I hope you can see this little screen. So this is what his little sort of simple view of the physical perception of the universe through these recent times. In Newton's era, there was really the sense that there was a sort of a fixed space in which everything moved, and a great big rolling river of time that swept through all the universe in synchronism. And in that, there were particles, little billiard ball-like things like atoms. And I think Newton thought light was like that too, that everything was little things buzzing around in this great framework of space, swept along by the river of time. In the Faraday-Maxwell era, this idea of fields was sort of added to the picture. So that's what we've now got: space, time, fields and particles. And this was seen again quite as a sort of a real function really of space. Einstein comes along and space and time become space-time, and we've still got fields and particles. Einstein in 1915 sort of makes the gravitational field and space-time a sort of weird mixture. Now, what on earth a covariant field is, I don't know. But at any rate, I think it's sort of reflecting the fact that the gravitational field, according to Einstein, effectively was that space was distorted, that, if you like, the field and the space had really become one. And of course, it was space-time. So fields and space-time have become one, and we've still got particles tootling around in them. Quantum mechanics was happy with space-time, and again, had apparently managed to combine particles with some idea of fields, and I don't understand that either. The only quantum mechanics I'd ever come across really has just particles. But according to Monsieur or Signor Rovelli, quantum fields is the sort of generic description of things within space-time. And now his lot and other people, including my friend Jim Moffat, attending the Phyllis Tuckwell Hospice, but again, obviously a very serious mathematician indeed, are sort of stitching the whole lot together in these covariant quantum fields, whatever on earth that means. And so that's a sort of perception of how things have changed very strangely in, the last 100 years, really. Now, Carlo Rovelli sort of maintains that this is closer to reality, that these are all crude perceptions, and that gradually, as we've gone through this sequence here, we are approaching a truer perception of reality. And I suppose that's a point which I might presume to question slightly, because I suppose this is again sort of swapping into the sort of comparison with Christianity. Of course, in a way, our perception of and our talk about God is often very, very simplistic, isn't it? in terms of things we can understand. So just as we explain things here in terms of space that we see, time that we experience, particles, like we see things knocking around like billiard balls or waves, we talk about God as sort of have, you know, Jesus sitting at his right hand, or God, you know, covering, sheltering us under his wings, or, you know, you speak to God face to face, or all sorts of things which are sort of rather anthropomorphic, you know, i.e. in terms of human beings, human existence, human relationships, God getting angry, God. Well, in a sense, obviously all of those are rather simplistic. And of course, in parallel, there are sort of abstract views that have come along, perhaps paralleling some of these abstractions in the way we look at the universe that Carlo Rovelli was talking about. You know, we talk about, or theologians have talked about God not being a being like other beings, but is the sort of ground of all being, the absolute source of everything, personal and impersonal, all sorts of clever sort of abstractions to try and envisage the sort of inscrutability of God. But I think there's rather a telling little passage from good old C.S. Lewis, which I came across, talking about that, where he says, I'm talking about meeting God and the door opening to him. And then he says, this talk of meeting is no doubt anthropomorphic, as if God and I could be face to face like two fellow creatures, when in reality he is above me and within me and below me and all about me. That is why it must be balanced by all manner of metaphysical and theological abstractions. But, he says, never, here or anywhere else, let us think that while anthropomorphic images are a concession to our weakness, the abstractions are the literal truth. Both are equally concessions, each singly misleading, and the two together mutually corrective. So I think it is certainly arguable that old Carlo Rovelli's very abstract view of the universe is another concession to our what does he call it? Really concessions to our limited powers of understanding, and that just as really thinking about objects as being sometimes behaving like particles and sometimes behaving like waves, and we don't really know what they are, is just as valid as saying that they are covariant quantum fields with a whole string of equations behind them. Both of them are frantic efforts by our little brains to grasp something that ultimately is beyond us. And I suspect that what C.S. Lewis suggested about our attempts to, grasp the idea of God may well be true about our attempts to grasp the nature of the universe as well. And I feel if it's not rather presumptuous to talk about somebody like Carlo Rovelli as being a bit naive, I suggest that perhaps it's a bit naive to say that all of this stuff down here is closer to reality than this up here. So there we are. Now, fumble. How do I get rid of this? Stop share. Good, sharing has stopped because the window's closed. Right, I shall get rid of that. I shall stop recording. Stop.